Hello. So this video, I'm going to go over chapter 7, potential energy. In the video before, we have talked about work, and we defined what work is. Work is force times distance. How much force done the work contributed to move that object or move the system, right? And that represents the work. And work can be positive or negative. But also, work is a change of energy. Work is a change of something, right? Because you move, the object has moved due to that force applied. So you're changing something. That something is energy. So whenever you have a work done on a system, it depends on the work done by what force, but you always have a change in energy that relates to that particular force. Does that make sense? So we said, okay, there are different kind of forces, right? You have a gravitational force, you have a friction force, all those things. But let's say gravitational force that we're going to talk about mainly for this video. Gravitational force do work, but whenever you have a change let's say whenever the gravitational force does work, then you always have a change in gravitational energy, and we say gravitational potential energy. Let's see. So I'm gonna discuss. There is for mechanical energy or energy in general. Mechanical energy, we have typically when I say mechanical energy, that's sum of combination of energy due to a position, which is the potential energy, and energy due to its motion, which is kinetic energy. So object, if it's by being in at that particular location, possess some kind of a potential energy. And plus, if it's the object is moving, it also possesses kinetic energy. So some of those two energies is called, just in general, it's called mechanical energy. All right. And today we're going to just talk about potential energy in this video. I'm going to switch the screen into a whiteboard again. All right. Okay, so this is chapter 7. Okay. It's too small. Sorry. Chapter 7. Maybe I need to zoom in. 100%. Let me zoom in, and oh, it's pretty thick now. Sorry, maybe this is better. Chapter 7 again, and part 2. Oops, that's not what I meant. Chapter 7, part 2. Potential energy. Okay, so this is chapter 7, potential energy. I'm sorry, it's a little bit talking loud. Okay, so chapter 7, part 2, potential energy. First, you might hear, so this is, we're going to discuss energy, and I'm going to define the energies. Mechanical energy, before I jump into potential energy. Mechanical energy, when you hear mechanical energy, or people tend to just say energy, is a sum of two kinds of energy. So you could have an energy for different things, and you can possess energy. You can possess energy. Just put it smaller, and then make it smaller. Energy due to the position. So there's the energy due to the position. And that's called potential energy. That is a potential energy, but again, this is kind of a thick. So I'm going to change that size. Okay. This is called potential energy. So, and a typical example of potential energy is gravitational, potential energy, gravitational potential energy, and also elastic potential energy. Right? And there's a different kind of energy. The others were called energy due to the motion. And this is called kinetic energy. For potential energy, I use the symbol like this, PE. Kinetic energy, I'll just write it KE. So mechanical energy is, so you can see, is equals to PE plus KE. All right. So you can see that just there's by object that's being there at that location possess some kind of energy because it's in a, if it has a force applied, and to be there, there's a force applied, and to be there, you have a potential to do work. So that's what we call potential energy. For example, so the gravitational potential energy is that you're here, but then there is a force applied, gravitational force applied, right? And then when I let go, my hands fall down, and that's due to the gravitational force. So if I don't go, just being at this location, it has a potential, gravitational force has a potential to do positive work. So the more higher you are, you have more and more potential to do more work, right? Because you can, as the height increases, you have more, you can, the force can do more work. Elastic potential energy is that you have a spring, like this one is a spring, right? And if I pull it, spring, right? If I pull it and I let go, I let go. So by being this, by pulling it here out from this, its natural length, now at this location, this one has a potential energy to do, for the elastic force to do work. Because if I let go, the spring force, the elastic force will take this back into the opposite direction as I pulled. And so it will do, the spring force is going to be pushing it, so it's going to do a positive work again. So due to these two forces, different kinds, these two gravitational force or elastic force, being in a location with these forces, you have some potential energy. Kinetic energy, I'm going to define it later in another video, but it's the energy of motion. So when the object is in motion, you have some kind of a kinetic energy, and a mechanical energy is to describe this sum of these two energies. So that's the mechanical energy. And here in this video, again, I'm going to be talking about focusing on the potential energy, especially the gravitational potential energy, because we haven't really talked about elastic force too much. Okay, so let's move on to a potential energy. PE, okay. Is work a scalar or vector? Right, work is a scalar. So therefore, and the work represents the change in energy. Work done by the gravitational force represents the change in gravitational potential energy. And therefore, potential energy is scalar. And you use unit, joule, just like the work. Okay. Let's say, so potential energy is due to its position. I give you an example. Let's say, so this is a spring, and then I'm holding it. I stretch it, right? So there's a pull force. I pull it into this direction. That means there is this much delta x has moved. And as I pull the objects against the spring force, that means the spring force is applied onto this direction. So you see that work done by the, let's see, work done by the pull force, that's equals to F pull and what? F pull times what is it? Yes, it's the displacement, right? So how much this force has done the job to move this object, and that's in parallel to each other in the same direction. F pull is in this way, delta x is in this way, so it's positive. But at the same time, this object has it's connected with a spring. So when you're pulling it, there's constantly there's a spring force that's applied. So spring force also done the work. F spring and delta x. But you see the spring force is pointing into this direction to the left. Backward, it's a restoring force. You always want to, it always applies in the opposite direction as you're pulling, right? And then the delta x is stretched, so it's moving to the right. So therefore, this is negative. And I'm going to write it, you guys don't know, so this is actually dx. And then we have to take the integral from x1 to x2 to be precise. Because spring force is not really not really linear to, it's not constant. It changes how much your stretches, and depends on the location, it changes the value. So you have to actually take the integral, but don't worry about it. It's just what I want to say here is that it's negative. So when the pull force is done a positive job on the object, at the same time, the spring force is doing the negative work. By doing the negative work, right, done by the spring force, we are increasing or storing up an energy to do a positive work. Because you see, if I let this ball go, you stretch it, stretch it, stretch it, stretch it. So your stretching process is going to be negative work done by the spring force. But once it's stretched, now it's stored up so much potential energy that now the spring force is ready to do positive work. All right? So negative work done by the spring force implies increase in positive, increase in a potential energy. So let's see. This was a little bit thick, so I'll change to this size. So this negative work done by the spring force implies increase in potential energy due to the elastic force or spring force. This is the same thing as a spring force, right? Force. So doing the negative work, it means that it's storing up an energy. Therefore, increasing potential energy. Because once you let go, what happens is that you let go, you let go, then this one is going to shrink. It will move back. Delta X. Due to the spring force, the red. Spring force is going to bring this ball back. So then it will do the positive work. Does that make sense? So you can see the negative work done by those spring force or gravitational force means that you have an increase in potential energy, because now you have a potential. You're storing up the energy by doing more and more negative work, and then you go up, then you have a higher potential energy to do the positive work. So at that state, when you're at the high location, or when you're stretching it, or compressing it, you're storing up an energy. You have a more and more potential energy, and once you let go, it'll lose it, but then it will do the positive work. So that's what the potential energy is. By being in that location, you feel like you have tensed, right? Okay, I have more, spring force applied by stretching it, or you bring the bowling ball all the way up higher and higher and higher, right? Just being at the high location, there's some sort of excitement, because you can predict what would happen. It's going to give a big positive work due to the gravitational force or due to the spring force. So another example that I'm just, red, no, I don't want to have a red, is the bowling ball, right? This bowling ball. You're holding it. So you move it up high from the ground. By moving up high, so this process, right? This process, work done by the gravity is negative. And that's going to be force of gravity times delta y, and but its force of gravity is downward, delta y is upward, so it's going to be negative, and then force of gravity is mg, right? And then you wrote it up by h amount, so it's the minus mgh. But then once you're there and you let go, when you let go, then you're going to have this you're going to have this gravitational force will do a work that's positive, because it's going to move, now it's going to move in a downward direction. Delta y equals h, and now the gravitational force will do the positive work. And then what happened? It's gonna, if it hits your, this bowling ball, it's gonna hit your leg. Right, it hurts. The higher it goes, the higher you bring the bowling ball up, you do more gravitational force that's more negative work, and it stores up more energy. It stores up more potential to do the positive work. Then once you let go, the gravitational potential energy will be lost as it goes down lower and lower and lower. But you're doing, because you're doing the positive work, right? And then it hits the longer that you move, you do more work, so it hurts more. So you see that work done by the gravitational force is Fg, and then it's always have to be in the y direction, vertical direction. And then negative, so when this is negative, implies the increase in gravitational potential energy. If it's a positive, then implies a decrease in gravitational potential energy. So you see, you really see, I hope you see that this thing, work, is a change in energy. And specifically, work done by the gravity is equals to the change in gravitational potential energy. And you see that, what is it? To find work done by the gravity though, work done by the gravity, right? That's equals to changing gravitational potential energy. And that's Fg times delta y, I say. And then if it's a same direction, it's positive, it's that direction. So the positive or negative, it's going to flip, but let's just keep going. So then this Fg, which is the gravitational force on the object, That's also the same thing as the weight, and is equals to mass times gravitational acceleration, right? Fg is mg. Mass times the gravitational acceleration, 10 meter per second square, right? Mass times 10 meter per second square. Times the height. So here, from here, we can say change in potential, gravitational potential energy is mgy. And then typically people just say mgh. So that's how much the gravitational potential energy is. It's mgh. Notice that though, right? This is the key. Delta y and a delta. So one thing is that for gravitational potential energy, potential energy. We're always discussing about change. Right? Because the work is a process, how much it changed. So you have to have an initial and a final, right? To talk about work, you have to have the how much it moved. So it moved from one location to another location. So gravitational potential energy is, you can find it by talking about work done by the gravitational force. So the higher you are, you do more work, more negative work done by the gravitational force. So therefore you have a more potential energy, but that's comparing to the bottom where it's moved from. So you always have somewhere, it's moved from somewhere to somewhere. We always talk about the transition, how much change. And so we just said that delta H, right? This delta Y or H is measured from the floor. Then we set, what we're doing is that we're setting the y equals 0 at the floor. But as long as you talk about change, it moves from one location to another location in a vertical direction, because gravitational force is always just vertical direction. Then the initial can be anywhere. There's no such a rule that it has to start from the floor. You could be moving the object from third floor to the fourth floor, let's say. Then you have a different change in potential energy, right? What if I'm discussing about this, doing this demonstration so maybe let's say currently I'm in the office and my office is in higher altitude than Santa Monica College, let's say. And then talk about this pen is fell, move whatever from distance 1 meter up high from the floor and down. But that's going to be the same amount of change in potential energy, 1 meter floor from the floor in a Santa Monica College, even though I'm starting altitude that's higher, let's say, right? So it's just a change. You could put the initial anywhere. You decide to put the initial at anywhere, and typically you put the initial location to be, this is it, set. You decide. To be on the floor. You could be putting the y equals 0 at the ceiling. You could be putting y equals 0 at the second floor. You could be putting a y equals 0 down below. Anywhere can be y equals 0. You decide. but conveniently, typically we just put it on here. So I could just say, I'm holding this pen right now here, right? And then I could just say, okay, this one could be, what's the weight of this pen? Maybe I'll say 200 grams, let's say 200 grams. Let's say has 200 grams, so 0.2 kilogram, right? Times 10, so it's like a 2 Newton. So the gravitational force is, let's say 2 Newton. And then, but I could be saying like this pen currently have 10,000 joules. Can you? Does that make sense? This, I'm holding a pen. This pen has a gravitational potential energy that's 10,000 joules. Can we say that? Yes, we can. And let's, if you're not sure, we'll again discuss this in a discussion. Okay? You need to take a note. How's that be possible? And you should be able to explain it if I ask you that in a discussion. Okay. Let's see. So again, the change in potential energy is the opposite to the work done by the gravitational force. So let's say, again, different example. There's an object that has a mass here, and then it's brought up upward. Initial, final. So it has moved, let's say, distance h, right, upward. So the change in gravitational potential energy is mgh. Force, this is the force of gravitational force times the h. Let's see, what if I move this ball exactly the same mass, but instead of moving vertically up, I'm going to use the ramp. Okay, instead of that, so I use the ramp. So it's the same mass, it's the same mass. Same height, same change in height, same change in height. But used a ramp. So walked longer distance. So you walked a longer distance to reach the same height because you're not directly bringing up height. What is the change in the gravitational potential energy in this case? See, the gravitational force is always vertically downward. This is Fg. And we say work is only the component that's parallel to each other. So you could be walking the distance d along the ramp. So it's a longer distance, but all we care is the parallel component to each other. So all we care is that displacement. So this is the displacement vector, right? D. But then all we care is this part that we only care about. Because that's the part that gravitational force is actually responsible for doing any work. So at the end, this is going to be equals to what? This is also equals to mgh. Remember Fg does no work on, sorry, Fg does no work on horizontal direction. Gravitational force is always vertically downward. So if you have a motion that's perpendicular, horizontal motion, gravitational force does no work. So the only thing that we are interested in, the gravitational, how much work done by the gravitational force, is only the vertical component that's either parallel or anti-parallel. And then if you're bringing up high, even though you walked on the ramp, that's a longer distance, what it matters is how much change in height. That matters. Only the vertical component, the vertical displacement, that matters when we discuss about gravitational potential energy. Okay? So let's say this is the case A. Right, still the same. So it's change in potential energy is the same. Because they only moved, at the end they only have the same change in a height. But why do we sometimes use a ramp? If you have let's say you're carrying a heavy items, rather than bringing up all the way up high, vertically up high, sometimes you prefer using a ramp, right? So it must be doing something different. What is it? So in B, so for the ball to move up, so to push this ball up high to the location of H, we know that changing gravitational potential energy is mgh. This is the amount of work you need to do to bring the ball up high. But let's talk about how much force work done by the force to bring up this ball up high. Then the force F, which is you're putting it along, this one is along the ramp, right? So that's F, that's along the ramp, times the displacement on the ramp. This should be also same as mgh. That's how much the potential energy has changed. And you know that this distance, d, is longer than h. So therefore, this F parallel has to be smaller than mg. So it requires less force, but longer distance. To have the same effect. Does that make sense? So when you use the ramp, the work you're doing is the same. Either you're bringing up vertically up high or going along the ramp. The work you do at the end is the same thing. You could just bring it all the way vertically up or along the ramp. But by walking the longer distance to get to the final location, the same final location, you do less, you don't need to push as much because you have to walk longer distance. So, okay, sure, you have to walk a longer distance, but you don't need to push as much to give the same result. So, knowing that, okay, I'm going to leave the video with these questions. If you have the stairs, that's it. And then I'm bringing the mass of the ball up here. So this is going to be the final location. So I have brought it up height h from the floor compared to the same initial place, but I'm bringing directly up. Compare the gravitational potential energy. Which one has the more which one has more increasing gravitational potential energy? Which one has more work done by the gravity going through this process? How about this? So same mass m, now it's moved for longer distance d. What is the gravitational potential energy? In this case, it moved for a distance d. So these are the questions. And then this one too. You should be able to understand this. Yeah, so I'll leave it up to here for the gravitational potential energy, right? So go over this star examples, at least 3 of them, and also make sure you understand the definition. And if you have any questions, you could ask me in a discussion. Okay. We might go over, if I can find more example problems, I'll do that. All right. So I hope you enjoyed the potential energy. And so again, increasing, doing the negative work done by the force, it's either elastic or gravitational force means increasing potential energy. Decreasing potential energy is that it's doing the positive work. Storing up energy so that it can do positive work. All right. So see you later in the class.